Welcome everyone to another seminar of Physics Latam. Today we are very happy to have Professor Wei Song talking about singularity theorems. She's a professor at the Yale Mathematical Science Center at Tsinghua University. Her focus is on theoretical physics, including string theory, quantum gravity, and holography. Song obtained her PhD at the Chinese Academy of Science, followed by postdoctoral research at Harvard University and Princeton University. Throughout her career, Song has made significant contributions to the understanding of holography dualities, particularly in space-time. There are no asymptotical antecedents, such as the Kerr-CFT correspondence. Her research also delves into holography entanglement entropy, the SYK models, and integrable irrelevant deformations. Song's work is influential in the field of quantum gravity. Please remember to raise your hand at any point if there is any question. And now I leave you with Wei Song. Please go ahead.
Thank you very much for the nice introduction. It's a great honor and a great pleasure to give a seminar here. I was told that this is some sort of extended lecture for students who have finished a semester of JR. So this will be hopefully pedagogical, and so I will start with the most basic. So our topic today is singularity theorems. So the basic question is the following. Assuming there are some physically reasonable conditions. Well, what do we mean by reasonable conditions? I will specify later. And basically, they are the causal conditions that you impose to the space-time topology and some causal structures, and also energy conditions that characterize some matter, the property of matter distribution. And then with these assumptions, will the evolution of Einstein gravity lead to singularities? So in the following, we'll basically go to the following four main topics. First, I will introduce the physically reasonable conditions, namely energy conditions and the causal conditions. And then we'll go to the discussion of geodesic congruence and rotatory equations. And then finally, we will go to various versions of singularity theorems. So as you can see, I highlighted singularities. And in my outline, I said that I'm going to talk about the geodesics. So what does this geodesics have to do with singularities? Well, I have to first explain what we really mean by singularity before going on with all these discussions. So what would you think would be the natural definition of singularity? Well, we'll learned some examples of spacetimes, like Schwarzschild or black hole. There are in the metric, in the Schwarzschild metric, there is a component that diverges at the horizon. There is a singularity in the metric component. We certainly don't want to call that as a physical singularity. And naturally, we would expect that a physical singularity would necessarily mean that there are some points in your space-time where the curvature goes to infinity, or in some other cases, the metric is not sufficiently differentiable. That means that some derivatives of the metric will blow up. That would be some natural guess of what we would mean by singularity, and that's very reasonable. But what I want to use, or actually what the singularity that rarely show up in these singularity theorems are not these singularities that are directly related to properties of curvature. What will show up is this so-called geodesic incompleteness. What's that? It means that these geodesics, or there are geodesics that will terminate at a finite or fine parameter. So more explicitly, it means that there are geodesics. These geodesics we can extend its affine parameter and make it maximally possibly extend its parameter, at least in one direction, until it is impossible to further extend it. And in that case, we still find that this affine parameter is we can only have a finite range of affine parameter. So this is the meaning of geodesic incompleteness. So you can ask, what happens to the curvature if a space-time is a geodesic incomplete? Well, there are several situations. The first possibility is the most natural one. Is it has the so-called scalar polynomial curvature singularity. So one example is that the Ricci scalar blows up at a certain point. This is the case for the singularity of Schwarzschild black hole. We know we can calculate. Sorry, this is not the case. There are some. An example of that is let's say this if we have a cone geometry and there if there is a conical deficit, then this scalar curvature blows up there at the cone. And of course, there are, this is the first example, scalar curvature. If the Ricci scalar blows up, it is, of course, one example of scalar polynomial curvature singularity, but there are other possible scalar polynomials that you can construct from this Riemann tensor. For example, we can have R and R mu nu lambda sigma R mu nu lambda sigma. This is quadratic in the Riemann tensor. We can construct lots of such polynomials. They form a scalar, but they are polynomials of the Riemann tensor. And sometimes it also contains some further derivatives. The second possibility is that it's called the this parallelly propagated curvature singularity. That it means that components of the Riemann tensor or its covariant derivatives along a parallelly propagated tetrad blows up along the geodesic. This is sometimes called this PP curvature singularity. If none of these happen, but yet there is a geodesic incompleteness, then well, we call it this non-curvature singularity. So of course, there are once you know the space-time has a geodesic incompleteness, it will be nice to further know whether a curvature or singularity exists or not. But the singularity theorems we are going to discuss today is mainly about when will geodesic incompleteness show up in space-time. Okay, with this clarification, we'll go on to these conditions. We'll first consider energy conditions. So as we know, Einstein's equation relate space-time curvature and matter stress tensor on the right-hand side. So now let's assume we consider a space-time, and we can have this tetrad formalism at each point on the space-time. We can consider also normal basis called the tetrad. So that's label this tetrad by this label A, B, and each tetrad is a vector in space-time, and they satisfy this also normal condition, namely if you contract the inner product of EA and EB using the metric space-time metric G mu nu, it's just eta AB, where eta AB is Minkowski metric. So we can consider a decomposition of the stress tensor using a tetrad, and by choosing cleverly of this also normal basis, we can assume the stress tensor can be diagonalized. Then this diagonal components of the stress tensor. So if we write the stress tensor in the matrix form in this diagonal basis, its diagonal components are given by, well, let's put it this way, are given by this time component is minus rho, where rho is the energy density, where the other diagonal components, Pi, are the pressure, are this so-called principal pressure. These are the eigenvalue of the stress tensor in the spatial directions. There are several useful examples of that. Consider the simple example for a perfect fluid. We know for perfect fluid, it's isotropic and homogeneous. And then in this case, this all the components of this pressure are the same, and they like P1, P2, P3 denotes the three diagonal components of the pressure. We can also consider this thermal radiation, massless thermal radiation. When it is massless, then the stress tensor has to be traceless, and then in that case, this pressure equals to a third of the energy density. And there is also the dust. Dust means that there is no interaction. That means that there's no pressure, and therefore all these P's are zero. And also this dust has positive energy. This is the ordinary dust, has P equal to 0. We can also consider the so-called null dust that mimics radiation, and in that case, the stress tensor can be written as a coefficient rho, where again it is the energy density times K is the null vector. That is for the case of null dust, the stress tensor is just proportional to rho times K mu. And you can check if you consider Einstein gravity coupled to this Maxwell field, and you can just write down the photon stress tensor, and you can check that indeed this stress tensor of the photon indeed satisfy the straightness condition and can be well described, approximated in some case by this massless thermal radiation. Okay, so this is after introducing or decomposition of the stress tensor, we are ready to consider various energy conditions. So we wish matter in the space-time are some sort of normal matter, physical matter that we are more familiar with. So that means that the behavior of the matter or the stress tensor has to be reasonable in some sense. So usually, how we want to compare the property of this stress tensor to the familiar stuff that we have observed in our real world. And the first energy condition that we are going to discuss is the so-called weak energy condition. So that for our intuition is that this for the stress tensor, if we do this decomposition, it better has a positive energy density, right? And then how do we make it more coherent, and how do we make it more universally stated? That is this statement of weak energy condition. So if that is to say that the energy density of any matter distribution as measured by any observer in space-time must be non-negative. So in JR, when we say an observer, what we have in mind is a normalized or future-directed time-lag vector. So when we measure stuff, when we measure energy, we can track the vector with our normalized future-directed time-lag vector. Let's call it V. Then how do we pick up this energy density? That is to do contraction of the stress tensor with this V alpha and V beta, and these in the case of say in this if it is diagonalized, we just pick up this energy density. But if this weak energy condition is true, then energy measured by arbitrary observer is non-negative. So this is a more general statement of our intuition that energy density is non-negative. Okay. In fact, we can by this requirement, the weak energy condition requirement, we can actually prove that if we decompose this stress tensor in this arbitrary tetrad, and then we diagonalize it and find the eigenvalues, we will find that this weak energy condition will imply that this energy density is greater or equals to 0. That's what we already expected. Furthermore, weak energy condition also implies that the sum of the energy density and all the principal pressure of each of them, and where I can be any of these spatial directions. I goes to 1, 2, 3. Each of them, the sum is non-negative. And so here I have written down some details. If you're interested, you can show how to prove it. But the conclusion is that this non-energy condition applies to arbitrary normalized future directed time-lag vector, and expressed in terms of the energy density and this principal pressure. It gives us actually 4 conditions. One is that the energy density is non-negative, and on top of that, the sum of the energy density and each of the principal pressure is also non-negative. Note that the pressure Pi can either be positive or negative. So these conditions are independent. So this is the so-called weak energy condition. Then there is this non-energy condition. So it is quite similar to the statement of weak energy condition, except that instead of mirroring the energy, or instead of contracting the stress tensor with the time lag vector, we require that the energy density measured by a future directed null vector is non-negative. So we replace this way that appeared in the weak energy condition by K, where K is null. We require T alpha beta, K alpha, K beta is non-negative. And then we can expand this null vector K on our also normal basis, and then by imposing this null energy condition, we get a condition on this energy density and principal pressure, and we will have 3 conditions. That is, rho plus Pi is non-negative. So from the consequences of the null energy condition and the weak energy condition, we can immediately see that if a space-time satisfies a weak energy condition, it also satisfies the null energy condition. In other words, weak energy condition is stronger than null energy condition. Okay, so these are the two energy conditions which we know one implies the other. Now let's talk about the third energy condition. This is called the strong energy condition. So, for strong energy condition, we still consider the observer or time-lag observer. So we still use V. Again, it is future-directed normalized time-lag vector. Now, as compared to weak energy condition, we don't contract T alpha beta itself to V. Instead, we can contract this combination T alpha beta minus a half T G alpha beta. This particular combination is greater or equals to 0. Well, why are we doing so? This is actually motivated by Einstein's equation. We know Einstein's equation relate the Einstein tensor, which is R alpha beta minus a half G alpha beta R to the stress tensor. And if we take the trace and then move the R to the right hand side, we get this Ricci tensor is precisely proportional to this particular combination of the stress tensor T alpha beta minus a half G alpha beta T. So again, we can expand this arbitrary time-lag vector, in this tetrad, and then we will find the following condition on the diagonal component of the stress tensor. That is this. It contains again 4 conditions. So we can see the familiar second condition. The sum of the energy density and each of the principal pressure are non-negative. Aside from that, we'll have basically the trace of the stress tensor, rho plus all the PIs is non-negative. Note that since the pressure is not necessarily positive, and this weak energy condition has precisely the same second condition, but for weak energy condition, we have rho is non-negative, and for the strong energy condition, we have rho plus sum of PI is non-negative. But this there's no direct relation between strong energy condition and weak energy condition. Strong don't be fooled by the name. Strong energy condition does not imply weak energy condition, and weak energy condition does not imply strong energy condition either. But of course, since strong energy condition also contains the condition rho plus pi greater or equals to 0, strong energy condition does imply the null energy condition. So that's the relation between null energy condition, weak energy condition, and strong energy condition. And finally, we would like to consider the so-called dominant energy condition. So the motivation is the following. So we expect matter should flow along time-like or now-vector field. So that means that matter's momentum density as measured by an arbitrary observer described by Wei is also a physical. It's also a futurely directed time-like or now vector field. So this this is this combination. We contract the stress tensor with this arbitrary time-like vector way. We obtain this basically this matter density, matter's momentum density, and this it is a condition that it is imposed to this this vector. It has to be future directed, time-like or now. So with this requirement, it implies two conditions. The first is that this vector has to be future directed. How do we distinguish time-like vector? How do we distinguish whether it is future directed or past directed? We consider the inner product with the time-like vector field V itself. So if two time-like vector are both future directed, then their inner product is negative. For instance, we consider dt, and the inner product of dt with itself is negative. So this is true for other time-like vector fields as well. So that requires this inner product. We require this minus T alpha beta V beta to be future directed. That means that this combination has to be non-negative. And then we also need this vector itself to be time-like or now. That means that the norm of this vector is non-positive. And then we again using all this algebra, you'll find that dominant energy condition implies that the energy density is no less than the module of each of the principal pressure. And this is true for each component of the pressure. We can also replace this the time-like vector V in this dominant energy condition by a now vector, and in that case, we will have this so-called now dominant energy condition. So putting all these together, we can find that this actually if dominant energy condition is satisfied, it implies that weak energy condition is satisfied. So recall, weak energy condition require that rho is non-negative, and rho plus pi for all of this pi are also non-negative. So it is obvious that dominant energy condition implies weak energy condition and further implies null energy condition. And strong energy condition, on the other hand, there's no direct relation between strong energy condition and weak or dominant, but a strong energy condition also implies null energy condition. So in short, here is the summary of all the local energy conditions that we have mentioned so far. Weak, null, strong, and dominant. And we can see that null energy condition is the weakest possible condition that we impose to the stress tensor. Okay, so it is later on we will use some of the energy conditions to prove singularity theorems, but you can always try to think about how is it possible to use the weakest possible energy condition to do the proof, and also I put local here. So local means that all these energy conditions are imposed to each point in space-time. And this is sometimes too strong. And in particular, when we consider quantum effects, it is impossible to impose such conditions, point-to-point conditions. So you also need to consider weighting these conditions. And in that case, there are several versions of finding the replacement. And one of this is called this average null energy condition. And there are further developments recently in that direction. I'll not talk about that today. Okay, so much for the discussion of energy conditions. Are there any questions so far? No. Okay, then I will go on. Now we will start to consider geodesic congruence and Richard-Doris equation. So what are congruence? Well, consider an open set O in a manifold M. A congruence in the open set O is a family of curves such that through each point in O, there passes one and only one curve in the family. So roughly speaking, we can just consider having a network, having several rays of these curves, and these curves will not intersect. That is to avoid this multi times, like the curve to pass a point multi times. So in the particular case, when we consider geodesic congruence, that is to say that we consider a family of geodesics. Let's consider in particular, this time-lag geodesics. And we can then parameterize each geodesic by its proper time t. And there it is a family of such geodesics. And so we can label each of the geodesic by a label S. So here is a picture of this. Each of this blue line is a geodesic. And each of them are labeled by different values of S. And then we can, along the geodesic, we can consider the tangent vector. And we know that by definition, this tangent vector has to satisfy the geodesic equation. That is to say that the covariant derivative contracted with the vector itself equal to 0. And if we further consider it has a unit norm, then this u, the norm of u is -1. So now we can parameterize all these geodesics by now two parameters. One is the proper time along the geodesic itself, and then S is the label to single out each of the geodesic. So from this diagram, we can see that we can consider fixed T and connect all the points along in the space-time with the same connect fixed time T, and connect all the possible values of points in the geodesic, and draw a curve to connect them. And that's these horizontal red lines. And this on these lines, we can also define this the tangent vector, and it's given by this the derivative, partial derivative of gamma with respect to the parameter S. And this is called the deviation vector. The meaning of the deviation vector is it characterizes how far away this neighboring geodesic are located at a particular proper time. So using the property of the tangent vector with unit norm, we can find that the norm, the inner product between the tangent vector and the deviation vector is a constant. Then we can just choose parameterization so that this tangent vector along the geodesic and the deviation vector is orthogonal. So this it is very interesting to study how this deviation vector evolve with time. So if we take the derivative, take the second derivative of this deviation vector, we'll find that it is given by the contraction between Riemann tensor and this deviation vector itself. The right-hand side is linear in the deviation vector itself, and quadratic in the tangent vector of the geodesic. So this is called the geodesic deviation equation. And we can define this two tensor B alpha beta, which is the covariant derivative of the tangent vector. We can see actually this two tensor is spatial in the sense that it is orthogonal to the time-lag vector U. It is the contraction of each of the index is 0. And this can be shown by using the geodesic equation and the fact that U has unit norm. Using various properties of these vectors, we can also or the definition basically, we can show that this the deviation vector, if we transport it along the geodesic, it is 0. And similarly, the Lie derivative of the deviation vector on the tangent vector of the geodesic is also 0. And using this fact, we can show that we can show that the covariant derivative of the deviation vector contracted with the tangent vector, and this is basically the characterize whether this vector is parallelly transported along the geodesic, whether it is 0 or not. By using these properties, we will find that this quantity, it is proportional to this tensor B. It is determined by this tensor B multiplying this eta. So as long as B, the tensor B is not 0, it means that eta, the deviation vector, is not parallelly transported along the geodesic. Okay, so using so now we can recall what we have done. We have a time-lag geodesic congruence. We have defined tensor, which is the covariant derivative of this tangent vector. So we can actually study the key properties of this tensor B, and we can decompose it into basically a trace part, a traceless symmetric part, and an anti-symmetric part. This can be done in arbitrary space-time dimensions. And in order to do so, it is also useful to define a space-like metric, HAB, which is basically we single out, roughly speaking, single out the spatial part of the metric by adding GAB by UAUB. And then this H is actually a projection operator, and it actually projects components to the of a tensor to basically project the spatial part of it. So the expansion basically the tensor B alpha beta can be separated into the so-called expansion part, shear part, and twist part. So the expansion part is essentially just the divergence of the tangent vector, and the shear part is the traceless symmetric part. Is to take the symmetric part of this B tensor and subtract its trace part. This combination is the trace. And then the twist, or sometimes also called the rotation, is denoted by omega AB, and this is the anti-symmetric part of this B tensor. Okay, so to give you some intuition, let's just consider this three-dimensional, 3+1 dimensional space-time where the time direction is orthogonal to the three-dimensional part. And then we can consider the time-like congruence whose tangent vector is just dt. Then we can consider the decomposition, 3+1 decomposition by singling out this, subtract out this time part and get this, the spatial part is just a Jij, that's just H. And then we can calculate the variables that we have defined. The expansion. The expansion, as we mentioned, it is the trace part of this B tensor, or alternatively, it is just a divergence of the vector U, and that we can directly calculate using the metric here. And it turns out that this expansion is just the rate of the change of the volume, the spatial volume, which is in this case the determinant, square root of the determinant of the spatial metric divided that way. So that's the meaning of this expansion. So it actually characterizes how the volume, how the volume will change along the flow of the geodesic. So if we this data is positive, it means that the spacing between these curves are growing. That means that this congruence will be diversing. Alternatively, if theta is negative, then this congruence will be converging. In various special cases, this theta, the expansion, goes to -infinity. And if that happens, we see we reach caustic. It is also called a focal point and or conjugate point. This is a very important quantity, and we need to use it later in our discussion. So to give you some further intuition about what this expansion, shear, and twist mean, we can consider the case where the spatial directions are two-dimensional. In this case, we can just consider this expansion. Expansion, as we mentioned, is the trace part of this B field, and what if we consider this flow of this curve along T, then this deviation vector will change from like T from the initial time T0 to arbitrary later time T. So what after this time delta T, then this deviation vector will change by delta 8 alpha, which is given by applying this deviation geodesic deviation equation. So for the expansion, it's just the fractional change of the area per unit time, and then the shear is what the shear is doing is to stretch or squash the length in different directions, but still preserve the area. So expansion will change the area, but shear and twist, they will both preserve the area. What twist is doing is to rotate rotate the vector. That's why it is also called a rotation. It is also useful in later discussions to consider this the case when a time-like geodesic is hypersurface orthogonal. If by Frobenius theorem, we know that if a vector field is hypersurface orthogonal, then we can find a scalar field F such that the vector field is proportional to the gradient of this scalar field, and then this implies the following combination equal to 0. It's this square bracket means totally anti-symmetric in this indices alpha, beta, and gamma, and this is to take a covariant derivative with beta. So for a time-like geodesic, then hypersurface orthogonal will imply that this the rotation or twist equal to 0. So why is this relevant? Well, now it comes to our very important equation, the so-called Richard-Dury equation. So the Richard-Dury equation is to consider this derivative, the derivative of this B tensor with respect to the proper time. So by definition, we know that can be written as the contraction of the covariant derivative with respect to coordinate alpha, and then contract with the tangent vector. And by some algebra, after using the fact that U is a time-lag satisfy the geodesic equation and it is unit node, we'll find that this derivative of this B field can be written as a quadratic contraction of the B field itself, and a term which is the contraction between the Riemann tensor and this tangent vector itself. And if we take the trace, recall theta, the expansion theta, is the trace of this B field, right? So if we take the trace of the equation above, we will find the following. The derivative of the expansion with respect to the time t can be written in terms of the expansion. Well, we can see it is quadratic in the expansion, and actually it is a perfect square, and also a quadratic term in the share, and also a quadratic term in the twist. And finally, a term which is the contraction of the Ricci tensor and U itself. So this is the so-called Richard-Doris equation. This is called the Richard-Doris equation. And we mentioned earlier, just a few minutes ago, when we consider a congruence of time-lag hypersurface, a congruence of geodesic data orthogonal to time-lag hypersurfaces. The geodesic itself is time-lag. It is orthogonal to space-lag hypersurfaces. So if we consider such a situation, then we just learned from Frobenius theorem that the twist equals to 0. This is by Frobenius theorem. Then now if we further require strong energy condition is satisfied. Do you still remember what is strong energy condition? Strong energy condition is the combination of the stress tensor with its trace, so that by Einstein's equation, this is proportional to Ricci tensor. And if we assume strong energy condition, then by Einstein's equation, this means that the Ricci tensor contracted with two time-lag tangent vectors will be positive. So using these two conditions, time-lag geodesic is hypersurface orthogonal, and a strong energy condition, we find the following. So the derivative of the expansion with respect to time is non-positive. The reason is that all terms in the all non-vanishing terms in the right-hand side of Russell-Doris equation are all non-positive. Well, this is obvious for the first term because it's theta squared, and it is also obvious for the second term. Theta alpha beta is the traceless symmetric part of this tensor B, and this is just it's squared. This is also positive, non-negative. And then the last term is given by strong energy condition, and this term vanishes due to the Frobenius theorem because we required hypersurface orthogonal. So this is the so-called classical focusing theorem. So what does it mean? Well, it means that if strong energy condition holds, then gravity is attractive because when theta, recall that when t increases, we are going to the future, right? Theta d theta dt is non-positive. It means that as time evolves, the time-like geodesic, they are converging. So this geodesic is convergent because, well, gravity is attractive. Yeah. Okay. So we can go further. We see the non-vanishing part of the right-hand side of Russell-Doris equation. It is as follows. We see each term of them are non-positive, but this means that the right-hand side has a maximum value that is given by the entire right-hand side part can be no greater than the first term, right? So we have an upper bound for the derivative of theta, and then we can actually integrate this inequality. We found the following: the inverse of expansion as a function of the proper time is bounded from by the sum of the initial value at say certain time, some initial time, and a linear term in time. So if initially this theta naught is negative, then we can say that as t goes to as t increases, then the right-hand side will reach 0. And recall that this is the inverse of theta. That means that within a finite proper time, which is bounded by this initial value theta naught, within such a finite proper time, the expansion will go to minus infinity. That is to say that when this expansion goes to infinity, minus infinity, it means that all these curves, they converge to a single point. This is a picture where theta goes to infinity. This is a caustic. So acoustic is a singularity of this congruence. So we can have a simple example. This is the flat FLRW spacetime, where we can write this metric in terms of this this function of time a of t, and the Hubble constant is just the fractional change of this a function. And as we know, our observation so far have observed that Hubble's constant is positive. And this we know our expansion from our earlier discussion, it is just a derivative of v divided by v, and this is related to the Hubble's constant, a dot over a, and where capital D, uppercase D, is this space-time dimension, and this lowercase d is the spatial dimension. So what then with if we start this FLRW metric, we say that the expansion if we go forward, the expansion is positive. But if we on the other hand, if we go backward, that is to say, we go back to the past, then we'll find that this theta goes to infinity. It is that means that we without the assumption of inflation, everything comes from this Big Bang. So this is very intuitive argument that there is a Big Bang singularity there. But of course, we started with this FLRW metric, which was assumed that our universe is homogeneous and isotropic. But there's no reason to assume these symmetries. So more generally, we need to find a reasoning to say whether there is a Big Bang singularity or not, and this is given by this Hawking's singularity theorem. And in order to discuss that, we also need to impose certain causal conditions. So due to the time, let's directly jump to the condition that we really need. So what we really need is to consider a globally hyperbolic space-time. That's the causal condition we want to impose. Before that, we want to introduce the notion of a chronal. So consider a manifold M and a subset S in this manifold. It is a chronal if there's no time lag path in the manifold M that connecting different points in S. So usually you can imagine that a closed space-like surface is likely to be a chronal, but it's not necessarily the case of a simple example. A simple counterexample of this is to consider a cylinder. A cylinder is specified by spatial identification of the coordinate phi. And then we can consider a space-like surface defined by the equation T equal to epsilon phi. Here, epsilon can be very small, so that the surface itself is still space-like, namely the norm of it is time-like. So on this surface is this green line. It's the green wire wrapping around the cylinder. So consider 2 points P and Q. They are on this space-like surface, but as we can see, we can easily find a time-like curve to connect these 2 points. So this is an example of a space-like and closed set in a manifold M that is not a chronal. So in our subsequent discussions, we would like to consider chronal subsets. So let's consider closed and a chronal set S. Then we can define the domain of dependence. It is the domain of dependence is the union of the future domain of dependence and the past domain of dependence, where the future domain of dependence are all the points where every for each point every past inextensible causal curve through this point P will intersect with our set S. This is a cartoon for this domain of dependence. Sometimes we also need this notion of this I plus is the chronological future, and G plus is the causal future, and this chronological future of S are the points where are all the points that can be connected to points of S by time-like curves, where causal future is also contains points that can be connected to points in S by null curves. And of course, this future domain of dependence is a subset of chronological future and a subset of the causal future. Now, we are ready to define globally hyperbolic. So if a closed chronal set in a manifold M, if the domain of dependent is just the manifold itself, then we will call this set sigma or Cauchy surface. If space-time contain a Cauchy surface, then this space-time is said to be globally hyperbolic. Being globally hyperbolic, it means that the entire future or past of the universe can be predicted or directed from the data on this Cauchy surface. The Cauchy surface is also called this initial value hypersurface. And Cauchy surface has many nice properties, and in particular, if this space-time is globally hyperbolic, then all the Cauchy surfaces are homomorphic. That is to say that all the Cauchy surfaces in the same manifold M will have the same topology. And in particular, each causal curve in M will have a intersection point with this Cauchy surface sigma, and also a unique intersection point with sigma prime. So there will be a one-to-one map between the two Cauchy surfaces. And there are also other properties of globally hyperbolic spacetime. It is also stably causal. It means that you can find a global time function, and so that this you can choose this function so that each surface of constant f is a Cauchy surface. And then this space-time M can be just foliated by such Cauchy surfaces. And since you can do this foliation, then this manifold M will have the topology R times sigma. Sigma is any Cauchy surface because all of them has the same topology, and R is just the time flow. Okay, so there are many other causal conditions. Globally hyperbolic condition is stronger than the so-called stable causality condition. Stable causality condition, roughly speaking, is the condition is equivalent to say that you can find a globally defined time function. And this is also stronger than the strong causality condition. This is roughly to say that each causal curve cannot go infinitely close to itself. This is stronger than the condition that there are no closed causal curves. And there are also properties of globally hyperbolic, and in particular, if it is globally hyperbolic, then every point in the manifold can be connected to the Cauchy surface S by a causal curve of maximal proper time. And such a path is a time-like geodesic, and it is orthogonal to this Cauchy surface. So it's from the picture. So this is the Cauchy surface, and for any point P, of course you can draw multi-lines, multi-causal paths that connect P to a point in S, but this time-like geodesic orthogonal to S is the one that maximizes the proper time. And this curve, this geodesic will not have any focal points. And this statement is very useful in Hawking's singularity theorem. Now it's time to go to that. Okay, here is the theorem itself. So there are assumptions and conclusions. So what are the assumptions? Well, the main assumptions are the following. First, the universe is globally hyperbolic, and let's denote the Cauchy surface by S. And energy condition, right? We need to impose energy condition. Here, in Hawking's Big Bang singularity theorem, strong energy condition is assumed. And then the third condition is our observational data. So so far we observed that the local Hubble parameter of our universe is everywhere positive, right? So then with these assumptions, it means that there are incomplete time-like geodesic in the past. Or in other words, no time-like geodesic gamma from the Cauchy surface can be continued into the past for or indefinitely. It has to stop somewhere, and this proper time has an upper bound. Okay, so why is this true? Well, our first assumption is that the spacetime is globally hyperbolic. That means that every point P in our spacetime is connected to the Cauchy surface by a causal path, and this causal path has to have it maximizes proper time, and it is a time-like geodesic, and it is orthogonal to the Cauchy surface without any focal point. And the statement that it does not have a focal point is very important. Now, let's go to condition 2 and 3. We have shown before by if we combine Richard-Doris equation and this strong energy condition, we'll find that the expansion is the first Richard-Doris equation tells us the expansion is bounded is non-positive, right? And then we integrate and we use the fact of the initial data or Hubble constant is everywhere positive. Then we will show that this the expansion is less than d minus d times some positive number that is given by some observed data of the Hubble's constant. H mean is related to the minimum possible value of this Hubble's constant because we measure it locally. Then this Richard-Doris equation and Einstein's equation and strong energy condition, as we have shown, tells us that any past-going time-like geodesic orthogonal to S will have a focal point within certain amount of time, a limit amount of time. So how to combine these two conditions together? So we have seen that globally hyperbolic means that every point is connected by a causal or by a time-like geodesic to S without focal point. And then condition 2 and 3 implies that any past-going time-like geodesic orthogonal to S will develop a focal point within a finite amount of time. Putting this together, the only possibility is that this geodesic, this time-like geodesic, cannot be further extended. It is, in other words, it's this along there shouldn't be any point in space-time that goes to the past of the Cauchy surface by a proper time more than this bound. You cannot go along any causal path to that point. So to summarize, we see Hawking's Big Bang singularity theorem assumes strong energy condition. The universe is globally hyperbolic, and the observation that local hyperparameter of universe is everywhere positive. And then the conclusion is that there will be incomplete time-like geodesic. It will stop at somewhere in the past, and that's the Big Bang. Okay. This has the Big Bang singularity theorem again uses time-like geodesic congruences and strong energy condition, and we can the similar well, historically Penrose first had this singularity theorem. This is more related to black hole singularity, but the discussion of Big Bang singularity is more clean and clear. So we talk about that first. Then let's go to this Penrose singularity theorem, and it is the statement is as follows: if the spacetime contains a non-compact Cauchy surface and a closed future trapped surface, and we assume non-energy condition, then there will be a future incomplete null geodesic. So we can see several distinctions here, right? In particular, we see that we need to deal with null geodesics, and we need to assume a weaker condition, which is the null energy condition. Then we also need to introduce the notion of trapped surface. So let's go to that. Due to the time, we will jump. We have mentioned the notion of focal point in Lorentzian geometry, it is when we find the geodesic, we see that usually the geodesic extremely less this say the action of our particle, right? Or the proper distance between 2 points. But extremely less does not imply it maximus, right? So there is a condition. If when causal path will maximize this proper distance, and if it happens, then it implies that this for a time like geodesic, this geodesic will have no focal points. So this having a focal point is closely related to whether it is possible to find a prompt path. So what is a prompt path? Well, if we consider a causal path from 2 points Q to P, if it is prompt, then there is no causal path, causal path gamma prime that roughly speaking reaches reaches the place faster. So mathematically, say there's no causal path gamma prime from Q to a space-time point R, where this point R is near the point P, but is to the past of P. And in particular, if a point is in the boundary of the causal future of the point Q, then between Q and P, there is a null geodesic. And this geodesic gamma is actually the only causal path between P and Q. It cannot go inside Latam. Otherwise, some part of the path is spacelike, and it cannot go outside Latam either. And there are several properties for a path that is prompt. If it exists, it means that this point P has to be in the boundary of the causal future of point Q, and it has to be a null geodesic. And if we further impose this strong causality condition, this strong causality condition, let's recall, it says that a causal curve cannot go back to the neighborhood of any point multi times. So if with this strong causality condition, short enough null geodesic are all prompt. As later we are always considering globally hyperbolic spacetime, and as we mentioned, that's stronger than a strong causality condition. this will also true. This fact, short enough non-geodesic are prompt. This is also true for globally hyperbolic spacetime. And a prompt segment of our causal path can only be the initial segment. That is to say that consider a causal path. It is not always prompt, but it contains a prompt segment. If that happens, it can only be the initial segment. And strong causality condition also implies that every non-geodesic will have a prompt initial segment. And if a curve is prompt, it also implies that there are no focal points. Finally, if we say a non-geodesic is prompt, this non-geodesic it is ochronal. These two conditions are equivalent to each other. Okay. So just to summarize, if we say a causal path is prompt, it has to be a ochronal non-geodesic without any focal point. This is an important condition that we will use. And we can also discuss prompt path from a point P to a set W. So if a path, if a filter from W and P, if a filter going causal path from W to P is prompt, then it arrives, well, it means that it arrives as soon as possible. And the implication is that this causal path has to be ochronal non-geodesic. And if this set W is space-like, then this prompt curve has to be orthogonal to this set W, and it has the intersection point between this causal prompt curve and the W has to be at the intersection point. Has to be at this sorry this it is the curve, the prompt curve is orthogonal to is orthogonal to the set W at the intersection point. Sorry, I'm running out of time. So important property of this discussion of promptness is to consider this the boundary of the causal filter of this set W. An important conclusion is that the topology of the boundary of the causal filter of the set is the same as the initial value surface, that is to say, as the Cauchy surface. In particular, we know in Minkowski spacetime, the Cauchy surface is non-compact. And that means that for for the this boundary of the causal filter of W is also non-compact. So similar to the discussion of time-like geodesic congruence, we can also consider null geodesic congruence. And in that case, we can still separate the spatial part of the metric, and but since now the tangent vectors, now we need to introduce an auxiliary null vector field that's called N. Then so that this we consider this a spatial metric H alpha beta is roughly speaking the rank is D-2. It's then we can use this H alpha beta as a projection operator to project the spatial component of the tensors. So we can similarly define the expansion. It's actually it is the same as the divergence of this null vector, and so let's consider in the case a few examples where we can calculate this expansion. So consider a point in Minkowski spacetime. Then we can just take the null geodesic generator dt plus dr, and it is we can say the expansion is just this the derivative of the cross section area of this cone divided by the area itself. And in the case of a set W, then there are always two families of non-geodesic congruences. So for instance, if consider this W as this, then at each point, the light cone have the outgoing part and also this ingoing part. From this picture, we can see that the blue ones, the ingoing ones, they seem to converge, and the outgoing ones, they seem to diverge. And in general, the expansion for geodesic or non-geodesic congruence can be expressed as this infinite. Consider neighboring geodesic, and the cross section area between the geodesic and the derivative, that's delta A, and then the derivative with respect to the Orphan parameter of the non-geodesic, that's the derivative, and divided by this cross-section infinitesimal area. That's the general expression for the expansion. And now we can go on and write the null or Ricciardo equation that's basically the derivative of the expansion with respect to the fan parameter. And very similarly, we can see it contains 4 parts. Again, if this null vector is hypersurface orthogonal, then the twist part is also 0, and the right-hand side, well, we need to consider them term by term. The first 2 are still non-positive, and then we find the last one. The last one, we just need to require this to have a fixed sign, right? And it turns out null energy condition is enough because, well, because this is just the combination that appears in the null energy condition. So using null energy condition and this Reproduce equation, we'll have the classical focusing theorem. That is to say that the derivative of theta is non-positive, and again, if theta is 0 at some point, then this expansion will diverge at certain finite proper or certain finite fan parameter. So this is signals that there is some singularity. So finally, the notion of trapped surface. So what is a trapped surface? First of all, it is a codimension 2 surface, and it is a chronal and space-like submanifold of our space-time, and it has to, as we discussed before, normally there are in Minkowski space-time for such a codimension 2 chronal space-like submanifold, there are always 2 families of geodesic congruence. One has positive expansion, and the other has negative expansion. One is converging and the other is diverging. For trapped surface, the requirement is that both families have negative expansion. Both are converging, and this is called this trapped surface. So expansion of each family of orthogonal future-going null geodesics is everywhere negative. And there are examples of trapped surface. So we know Schwarzschild black hole, and inside the horizon, if you take a sphere as this codimension 2 surface, then you can check that both families of null geodesics are converging, and it is also true for the cross coextension. And here, this is the Penrose diagram of cross coextension of Schwarzschild black hole. The green curve is the Cauchy surface. And then in region 2, the black hole region, there will be trapped surfaces. And you can also find the Wadia solution, the trapped surfaces in Wadia solution. And now we can go to Penrose singularity theorem. So the assumptions are as follows. The space-time is globally hyperbolic, and there is a non-compact Cauchy surface. And we assume now energy condition, and we assume a classical instance equation is valid. Then the final assumption is that the space-time contains a compact trapped surface. And with all these assumptions, then the statement is as follows: the space-time is not fully non-geodesic complete. You always be able to find this non-geodesic that it has finite affine parameter. And this theorem applies to any spacetime sufficiently close to spherically collapsing matter to black holes in asymptotically flat spacetime. And due to the time, I won't be able to sketch the proof of this theorem. But if you're interested, you can look at the references that I give you. Last comment is as follows. So in the assumption, one of the assumptions of Penrose's singularity theorem is that there is a compact attractor surface, and you may wonder whether this is a physical assumption or not, and it's proven by Shen and Yao that given certain physically reasonable condition of the matter, then we do find that trapped surface will form. And so just to summarize, so the key thing that we have used is this Virtual-Duris equation, and we discussed the expansion. And there's in order to prove all these singularity theorems, we need to impose certain causal structure, causal condition, and energy condition. And we also need to assume that classical Einstein's equation is still valid. So with these assumptions, these theoretical singularity theorems has been established. And a final comment is, well, all this, both the Big Bang singularity theorem and this Penrose singularity theorem, they are both about both statement about geodesic incompleteness. So it does not directly say anything about whether or not there are, say, curvature singularities. And it is also interesting to find a statement, a direct statement regarding curvature singularities as well. Okay, I'll stop here, and thank you for your attendance, and I'd like to take some questions.